Okay. Holy. Right. So I should be able to hear. Yeah. Alright. That should be good. This is a recording. Of my kernel development journey thingy. I'll just play some music in the back. Okay. So I created a repository called Dionysios, which is the name of the Greek god called Dionysius, whatever. That's how the Americans or the Western people call it, but in Greek you pronounce it as Dionysios, something, or Dionysos. Anyway, let's git clone this repository, and we will in the folder Dionysos. Then we're gonna look at some things. First, I'm gonna add a reference section. This kernel is mostly based on the OS in 1000 lines tutorial. There you go. I do not want Olama. I really don't. How do I disable? I'm not smart when it comes to disabling stuff. Yeah. Chat. How do I disable you? I do not want you. Nah, whatever. I'll just leave it like that. So, reference first will be this link. Here. There you go. So, operating system in 1000 lines, and okay. Now, what we're going to be doing according to this document here. The basic functions of an operating system, especially kernel, are surprisingly simple. Even Linux, which is always cited as huge, was only 8,000. Today, Linux kernel is overwhelmingly large, but it started with tiny code bases like your Poppy project. We'll be implementing basic content. Hold on, let me play some classical music. Alright. So, and a disk device driver and file reader operation to see. Sounds a lot. Only 1,000 lines of code. That's actually pretty surprising. That is disgusting. That is disgusting. Anyway. So, one thing you should remember is that it's not easy as it sounds. Tricky part is debugging. You can't do printf. That's true. You learn debugging techniques. You never need application development. You capture channeling product like boot process page, but debug OS 2. Ha! This is good. So apparently this is gonna be a microkernel. Let me reply. This is going to be a microkernel based on this tutorial over here. So, the tougher the debugging, the more satisfying when it works. That's correct. So, you can download implementation examples. I'm not. I will write everything from the ground up. So, this project is not a copy and paste project. It will be handwritten, since it is more fun that way and I actually learn things. Okay, so I will say update readme. This is gonna be a thing that will span over a couple of months or weeks. So if I go back here, one thing you should remember is it's not easy as it sounds. The tricky part, can you understand? Yeah, okay, I heard that. This one available, CC, okay, on MIT license, Unix live environment. Yeah, I know C. In fact, we have the C here. The golden thing is good. All right. Hypervisor. Oh, I could also build hypervisor as well. So let's get started. This book assumes that you are using a Unix or Unix-like system. Okay. So this is gonna be in RISC V. I think it's gonna be 32-bit. Yeah. Let's build a new container for this. If it's the best thing to do or not, I could also use always my current. So what I need to do is install this thing. So we're gonna install with the apt package manager, but I don't think sudo works on this one. Maybe we could install with brew instead, because as here it says brew. We should have brew. So let's try that. That means that we can use I mean, in theory I could just open a dev container, yeah, in Dionysos, and then C kernel, no, C. I don't think it shows here. Bear. No, it's fine. We will use. So, what we're gonna do brew install LLVM, which is a compiler, and LLD, that's the linker, and then there's Kimu. We'll wait for it to install. I'll probably do like a couple of chapters for this one. Okay, then we can also, if it's Ubuntu, we can also install this one, but we're not gonna do that. Other OS users, that should be, we should have all that. Yeah. Check if your Clang, which is the compiler, supports 32-bit, so we're gonna check that as well. This is very cool. I love this. I fucking love this. I have no idea if doing this will get me a job, but I'm gonna do it anyway. Alright. Okay, so I go to my feed? Actually, while we're waiting, let's see what my people are doing. Okay, I'm not sure who this is. Who is this? Oh, well, I think I know him. I'm not sure. Chinese folk songs. I'll send this to my friend. Okay. Let's actually. I'm not sure if I should link this live to my Fedi post. Sorry, going through. I see. I found this YouTube playlist name. All right. This is gonna be my live stream on my channel, so we're just gonna put it there. Okay. All right, we installed everything, and so if I want to check Clang print, this is target, so the available targets for this compiler, and we're gonna select RISC-V 32. Yeah, there we go. Hey, there we go, works. So we should have this. All right. Now this is the Git repository. Oh wow, they even have me a nice Git ignore. Cool. This one I'll just replace that. Oh no, not really. I'm just gonna actually check. Disk. Okay, this is Dionysos build file. Let's not do copy and paste here. So disk. So anything in the directory, it's called disk. But we will apparently git keep dot map dot tar. Not sure if dot map. Linker is in here. Yes, so it's fine. It's already included. And then the output file. Object files are there. And dot elf, which I think is. Oh, there you go. It's an object file. Yeah. Bin is bin here. I don't think bin is here. Yeah, bin is not here. And log. Wait, is log? Yeah, no, log is not here. And then PCAP. Actually, what the hell is a PCAP? Store network capture. That's interesting. Okay. Cool. So let's read about RISC-V for a second. It is why I chose because specification is simple. We have the specification right here. It's trending instruction set architecture. Design decisions are well documented throughout the specs. We run an OS for 32-bit RISC-V. Yeah, so we'll work with this for now. QEMU. Computers are composed of various devices, CPU, memory, network cards, for example, iPhones. It is supposed to support QEMU vert machine, and we have this documentation over here. This is the QEMU. We'll put it here, put it aside for a second. I have all the supporting devices. This is great. No, it does not exist in real world. It's very simple and very easy, similar to real devices. You can emulate, QEMU for free. Don't need to buy physical hardware. When you encounter debugging issues, you can read QEMU source code. Source code, okay. Or attach a debugger to the QEMU process and investigate what's wrong. Alright. RISC-V assembly defines the instructions that the CPU can execute. It's similar to APIs for programming language specifications. Yeah, that makes sense. You need to write something. It's fine. I'm not scared of this shit. Compiler Explorer. Oh, this is the thing that converts into assembly. That's good. This is great. Let me put this in my tools. Programming low-level systems. That's great. Close this for now. Too many tabs open. All right. Assembly language, direct creation of a machine code. Yes. Add integer, right? Is it? Oh, is it add in assembly line single instruction? First column. This column here is the instruction name. This is the opcode, operation code. The following columns are the operands, the arguments for the instruction. The case adds the value 1, 2, 3 to the value in the register A1 and stores the result in the register A2. So it adds the value 1, 2, 3, A plus 1 plus 1, 2, 3, and store that value in the A0. Then we have registers, or like contemporary variables in the CPU. They are very, this is good. This is great basic CPU information. Reads data from memory to registers, does arithmetic operations, and writes the results back to the memory and registers. Yeah, this is good. Yeah, see? In common registers. I should print this out. Yeah, this is a program counter. This is the hardwired 0. Return address. Yeah, stack pointer. There you go. X5 to X temporary stack frame. That's a frame pointer. Function arguments. Return values. Okay, function arguments. Temporary register safeguards calls. Yeah, there you go. You may use CPU register. Interoperability with our software. How register is well defined. It's called calling convention. Yes. This is the calling convention, which is 4 pages long. I will print it out. Actually, this is actually really good. I'm impressed. Go print. You know what? I'll just bookmark this for now. Yeah. Then we have memory access. Registers are really fast, but they're limited in number. Most data are stored in memory, and programs needed for memory using the load word, store word instructions. So also LW and SW reads a word, which is 32 bits. A word. What is a word? Okay, this is very interesting. Not to be confused. In computing, a word is a fixed unit of data. There we go. By the instruction set or hardware of a processor. Yeah. So it's the size of a lot the registers and stuff. And storage in C. This would be load word A1 from the address in A1 into A0. So it's like A0 is equals to dereferencing A1, right? You know what? Actually, I should have pointers open. Yeah, it's, wait, no, hold on. X is equals to the pointer to PA. Yes, it's essentially dereferencing PA. Right. Hopefully the stream is still running. Yeah, that's good. So SW is store word. So load word is to read a word from the address. But SW is store it. Store a word in A0 to the address in A1. Store a word, okay, in A0. Register A, no, sorry. Is it address 0 to the address A1? No. Store word in A0 to the address. So it's to the address. Okay. It's all pointer dereference. Yes, it's A1 is a pointer. There you go. It's a pointer. We're dereferencing A1, okay, equals to A0. Yeah. Dereference. Store a word in A0. Store a word in A0 to the address. To the address. Yes, pointer. So we're storing a word. We're storing. So we're basically, hold on. Read a word. Yeah, something like that, I guess. You're just reading a word or a store word. A1, hold on. I have to refresh something. C, pointer, reference, D reference. It's dereferencing. It's dereferencing. P1 references C1. Means using the asterisk to retrieve the value from the memory address that is pointed by that pointer. So, values pointed by. So it's basically, so A1 is an address, and the the brackets is dereferencing. So it's taking the data that A1 is pointing to and store it in A0. There you go. Next, the branch instructions change the control flow of the program if they're used to implement if. Yeah. Okay, that's good. Oh, right. So B NES. Branch if not equal to 0. If A0 is not 0. If A0 is 0, continue. So it's just branching. So it's branching. And then we have function calls, jump and link, and then ret or return for calling functions and returning. So this one says load 1, 2, 3 to the A0 register, and then jump and link. So jump and store the return address in the RA register, because that's the return because that's the RA, because the RA register where is it? The RA is the return address. Okay. After function call, continue. So it's like that, and then we increment A0 first argument by 1. So we add 1 to A0 to A0, and then store it in A0. Sorry, and then we return the address stored in the return register. A0 register has the return value. So actually, what is the return address? What is the return address for computer? Value that indicate where a particular function should return control. Okay, is the address of the instruction following to the call instruction? Hold on, there should be a... Yeah. Okay. Return address. Yeah, so when carrying out function call, we need to save a return address, which is the address of an instruction following the call instruction. That we can assume the execution of the current instruction sequence. Yeah, there you go. View, show more, there you go. After executing, Okay, BLBLX instruction. Return address is stored in the link register for function return when the function is completed. So, BL function runs function A, and then it says, okay, we're terminating LR. Function PC change to function A. So the program counter is changed to function A, and the LR link register to the address of the instruction. Yeah, hold on. Is there a better okay, sequence of instruction console call to function A. At this moment, program stores the next instruction address, the one that follows the function call, into the system stack. The stored value is the return address. Program then jumps to that and begins executing some. Oh, okay, yes. So basically, when you run a program and then there's this function where you have to run, it saves the address, the return address. The return address is the instruction that follows that function, and then when the function ends, it knows where to continue. Makes sense. The stack, yes, stack, last in first out memory space, used for function calls, grows downwards. So stack grows here and heap goes here. The stack pointer goes top of so the top of the stack is here. Save the value into a stack. Decrement the stack pointer to store the value because the stack pointer goes downward. So if the top is address 100, we have to do -1, make it 99, and store it in there. Store the 99 address, 98, 97, and so on. So see here. Move the stack pointer because because we're interacting with the registers, right? It moved the pointer down by 4 bytes because -4 is 4 bytes, right? ADII, so add -4 to the SP, which is presumably 0. Let's say 0. Okay. Now it just adds to -4. So we just move the pointer down. If that is how it works. I don't know. Let's say it's 10, -4. Now that's 6. Now 6 we go to that address and we store. Yeah. Store A0 to the stack. Yes. So we're storing A0. Wait. So we're storing the address 0 to the stack. Yes. Yes. We're storing. Yes, wait, try to go back there. I'm sometimes very confused. Store a word in A0 to the address in A1. So this was like me saying dereference SP is equals to A0. Yeah! To load a value from the stack, load the value and increment the stack pointer. Oh, this is the pop operation. Oh, that's the push and pop operation. Stack operations. Oh, so in C, stack operations are generated by the compiler. See, this is how cool. This is you learning, right? You're learning how C works. This is great, right? So, load a value from the stack, load the value, and increment the stack pointer. Increment. So when you increment the stack pointer, let's say this is the stack, right? When we increment, we read. Right, there you go, and then we read things here. Yeah. How long is this stream now? Like, what fucking? How long is this? 32 minutes already, and I'm just still reading this. So there's CPU modes. Apparently, there's the M, which is the BIOS, the S mode, which is the kernel mode, and then the U mode, which is the user mode. Also here there are types called privileged instructions that applications or user mode cannot execute. In this book we use the following privileged instructions. Okay, so we have these instructions over here. CSR control and status register is a register that stores CPU settings. And we have a bunch of yeah. Oh, okay. So this is the instructions that when if the applications, okay, so applications are in user mode. Okay, it's where the applications operate. This is the executions that applications cannot use. For example, CSR, read from the CPU settings register, control and status register. Sorry, I have no idea where that is. Yeah, whatever. Fuck it. Yeah, cool. These are complex operations. To understand, reading the MS source code might be helpful. RVMU. Let me. Oh, interesting. Yeah, start. I do not subscribe to the idea that I'm writing this so that I can, have a job. I really don't care. This is fun. Now, in the following chapters, you encounter several C languages like this. It's inline assembly. I didn't know that. So you're writing inline assembly. Syntax for embedding assembly to C code. While you can write assembly separate file, you inline is generally preferred because you can use C variables within the assembly. You can assign results to the assembly to C variables. You can leave register allocation to C compiler. That is, you don't have to manually write preservation and restoration of registers to be modified in the assembly. Inline assemblies following the following format. ASM volatile. Yeah. Oh. Yeah. This is the assembly code. Oh wow, they even explain. Wow, this is such a good book. Assembly code originated as a string literal. Yeah, and then output operands. Okay. Store results of the assembly. Input operands, expressions used in the assembly. And then clubber registers whose contents are stored in the assembly. Forgotten see my own presumptive contents. Output and input operands are comma separated. Each operand is written in the constraint. These are used to specify the type of operand. Usually equals R register for output operands and R for input operands. Output and input operands can be accessed in assembly using. Oh, it's just like yeah. Okay, yeah. It's the value of SEPC CPU settings register using the CSR instruction and assigns it to the value variable. Yeah, makes total sense to me. This makes total sense to me. This writes 1, 2, 3 on to the scratch CSR. I really need to read this. Can I find the specs? Is this the ISA? I am reading the ISA. No, this one is the ISA. Oh, my apologies. So, address mapping. Yeah, here it is. CSR, does it have at least some kind of, yeah, there you go. Oh, this is unprivileged. Yeah, there you go. Step C, supervised exception program counter. Yeah, there you go. So there we go, we have it here. I wish I could print this as a book. This is great. Someone messaging me. I'm so focused. Anyway, yeah. So this is just writing registers, and I don't think we are able to remember every register. Written in inline assembly. Yes, the allies are automatically satisfy the orchestrating. Super convenient. Yeah, I agree. I recommend real-world examples. KNOS takes. Okay, so it's a compiler-specific extension. It's not included in the C language specification. Detailed usage C takes time to understand because constraints syntax depend on the architecture. Yeah, that's understandable. Okay, let's do overview. For starting to build an OS, let's quickly get an overview of the features we'll implement. Features in 1KLC OS. Okay. This book will implement the following major features. Multitasking, so multiple processes running to share the CPU. Exception handler, handle events requiring OS intervention such as illegal instructions. That's understandable. Paging, provide isolated memory address space for each application. System calls allow applications to call kernel features. Device drivers abstract hardware functionalities such as disk read write. This is good. And then file system manage files on disk and then command line shell. Oh, I could use my own command line shell for this. But anyway, so features not implemented. Interrupt handling. We use polling method. Yeah, that's okay. Interrupt. I'm not sure. Okay. Timer processing, multipolar processor. Yeah, that's okay. I'm not sure what my professor suggested. Yeah. Interrupt handling. We can probably do that later. Yeah, no problem. Timer processing. Well, use cooperative multitasking. Yeah, no problem. Multiprocessor. Yeah, that's fine. Source code structure, final structure will look like this. Okay. Common user library. Yep. Kernel shell. That's the command line shell. I think it's a very simple shell. User library functions for system calls, and then there's the user library. Yeah, we're gonna write shit into disk. Here we go. So, oh boy, it's gonna be pretty long, isn't it? Okay. When a computer is turned on, the CPU initializes itself and starts executing the OS. OS hardware initializing hardware starts applications. It's called booting. What happens before the OS starts? When the PCs, BIOS, and UEFI and modern PCs initializes the hardware, displays the splash screen, and loads the OS from disk. In QEMU, Virt Machine, OpenSBI's equivalent of BIOS/UEFI. Supervisor binary interface is API for OS kernels. Bot defines what firmware for an OS. Yeah, of course. Oh god, there's yeah, useful features such as displaying characters on debug console. SBI implementation is OpenSBI. In QEMU, OpenSBI starts by default, performs hardware-specific initialization. Yeah, boots the kernel. Yeah. Okay, so we'll start with a new file called run.sh. So we're gonna learn, I guess, how OpenSBI works. Set xue. Okay. And then this will be the QEMU file path. So QEMU system RISC v32. Yeah. And then we're gonna start the QEMU itself. Machine will be Virt. BIOS is the default BIOS, and we won't have no graphic. We want serial, standard input. Monitor will be standard input, and then there'll be no reboot. Yeah, that should be. Yeah, there you go. Switching QEMU monitor. Yeah. Start QEMU. No graphic. Yeah, makes sense. Okay, so if when we run this, I think I'm gonna run it in a separate terminal. So if I go Dionysos and then I do chmod because we need to make it executable. Shit, sorry. Run data switch. Oh, there we go. Let's boot it up. This is everything in here. This is good. We're running QEMU. Platform numbers for debugging processes. Press any key, nothing will happen because QEMU is standard input is connected to virtual machine serial port. Characters are typing. Are being set to no one reads the input characters. Press Control A, then C to switch to QEMU debug console. I think I'm gonna put this here. Control A, C. Oh, there you go. Debug console. Okay, and then we will quit. Easy, simple. Linker script. So this is the linker script in which we will use for our defines. So it defines the memory layout of an ELF file. An executable. Based on the layout, the linker assigns memory address to the functions and variables. This is because the linker will do that job for us, right? How long is this fucking stream now? It's 40 minutes. Yeah, I'll probably end this in like a couple of 20 minutes. So first, we're gonna make a kernel.link file, which will have entry. Okay, we will. Can you shut up? Fuck off. Like, just shut the fuck up. There you go. So the entry point of the kernel is the boot function. So the boot function will be the entry point, right? And then we're gonna define the sections. So, so we're basically laying out the memory layout of this file that is gonna be used. So the dot equals. This is the I assume this is the base address. The base address. So what is a base address, right? Yeah, this is good. Yeah. Hold on. Base address. Okay. OS dev wiki. Doesn't really say. Base address, register. So a base address. What is a base address? Reference point. This is what I used to do back in the day. This is very nice. What is a base address? Sorry. Yes, so it's the starting memory location or address of a data structure. Starting memory location of an address or address of a data structure. So basically we're defining that the start of our memory layout of this ELF file is going to be at this memory address. Alright. Yeah. Entry declares boot function entry point, then the placement of each section is defined in sections block. The text directives placed in the text section in any sections starting with places the .text section, and it says in the from all files. Okay, also the .current symbol is the current address. I see now. It automatically increments as data is placed, such as in the text statement plus equals this advanced current address by 128 kilobytes. The align for directive ensures the current address is adjusted to a 4-byte boundary. Allows BSS the current address to the symbol in C language in extern char. So text is code of the program. RO data is read only. Data is read write data, and then BSS is the section of read write data. That's initial value 0. Yeah, I'm refreshing this. This is good. So we will write .text. Okay. Keep then .text.boot. Actually, what does keep mean? Does it say the keep? It doesn't say anything about keep here. Yeah. Keep text boot. Yes. And then text.star. No. Dot read only. Yeah. So okay. Now we just define the text section. RO data, which will align. We'll make sure that it's a 4-byte. So 4 bytes. So .ro data dot that. Yeah, this is good. I'm not sure if there's a space there. Is there a space there? Yeah, it doesn't seem to be. Yeah, no space. So it's just that. So this is the RO data. So directive places the text section. Yeah. So we're basically placing the sections in .data. This is the data section. Align it for. And then the BSS section will be the current address. And then. Oh, sorry. Wrong one. So this should be the .data will be placed to .data. Then, can you shut up, sir? My God, I thought it's turning off already. Shut up. Then we will define the BSS section, which is align for. Maybe I should put it that way. Yeah, and then BSS equals dot. Yeah. Then place the BSS.star section .sbss sections, and then say that the BSS.end is now at the current address. All right. Then we say that the current address, align that current address to be 4 bytes, and advance, or basically add 128 kilobytes to this, and then stack top equals dot. Now, what does stack top mean? I don't think it says anything. But stack top basically saying that the top of the stack is now at this section, is now at the current address. That's all. Yeah. Kernels. Okay, so yes. Each section is placed in order. Yes, and the kernel stack comes after the .bss section. Its size is 128 kilobytes, and yeah, it makes total sense. And then, let's write some kernel. Okay. So let's write some kernels, yeah? Okay, let's add it linker file. Okay, so we write a new file. Oh shit, sorry. Which is because we already did all the memory layout, which is what the data will be stored in. We will now create the kernel. This is the C file now. So type dev. So we're gonna say type definition unsigned char uint 8t. Now what is a now if you refer to this, which I'm not sure if it's here. Yeah, type dev. Put this here. Yeah, this is let me write this down. Type dev storage class. Okay. It does not declare objects. Instead, they define identifiers that name types. So it's a type definition name declaration that attributes a type to each name among its declarators in the usual way. Thereafter, each such type name is just syntactically equivalent to its type specifier. Yeah. Yes. So basically, it's type B is long, type of B is long, and that BP is pointed to long. Yes. Okay. So it does not only synonyms for types that could be specified in another way. Yes. Basically, giving like an alias type thing to another type, right? Because like we don't want to write unsigned character or unsigned integer. Now, what is an unsigned signed versus unsigned? Unsigned int, okay. Signed char. An unsigned char is unsigned int is never negative, while a signed one is an int. Sorry, is a negativable int. Okay. So we're defining the types. Okay. Signed int uint 32. Okay. If we right, this is I'm gonna describe this. If we go to in C book, in K and R C book, section A8.9, type dev is basically an alias for a type. Yeah, this is why you need a book like this. Is very good. And then you do type dev, right, character, integer. uint 32 is size t. Yeah, so an integer int 8 is an unsigned character because a character in unsigned char risk 5. Does it say here? Pretty sure it does. Pretty sure it does say unsigned. Pretty sure it does say that. Yeah, it's fine. Whatever. I think for risk 5 unsigned char unsigned. Okay, so an integer. I just need to look at where they're an integer. Oh my god. Shit, you know what? Waste of time. Risk 5, risk V, integer size RISC-V 32. Integer registers C type int calling convention. Oh, huh. Oh boy. Okay, so the reason why it's 8 because it's 8 bits. Character is 1 byte in RISC-V. Yeah, I should print this shit out. I swear to God. And an int is 4 bytes, so it's 32 bits. Okay. Yeah. Size T. I forgot what type of size T. What's size T for again? What is this size T? Oh, it's for C size T. I forgot. It's an unsigned integer. Yeah, okay. It's basically used for. It's basically another type representing an unsigned integer, 32-bit integer. Okay. So extern char BSS end and stack top. Remember void memset. Okay, void buff. That's the buffer. Char, which is character, and then size T, which is n. Okay. This is so we're gonna use int. So we're gonna declare a pointer. Pointer to the buffer. Yes. Yes. While n, okay, is decreasing. Dereference equals C. It's pointer. I think there will be an explanation. Okay, so the kernel entry point, yada yada yada. Yeah, you know what? I'll just write everything down first. Okay, and then it's gonna return the buffer. Now, void kernel main. This is the main kernel function, and memset. We're gonna set the memory. Okay, so first parameter is BSS 0, which is the char size, and then followed by the size of the BSS end minus the BSS itself. 4. I think this is just a loop, infinite loop. Okay. Then we'll write an attribute section, which is .text.boot. This is supposed to be 2. Okay. Attribute. Oh fuck. Attribute section. Okay. Naked. I'm not sure why they use the word naked, but void boot void. Okay, so no taking, there's gonna be nothing returning it, and no parameters taking it in, and then we're gonna assembly volatile, because remember this is the syntax for writing inline assembly. Then stack top J kernel main, so it's gonna jump to the kernel main, then column, and then this is supposed to be a semicolon, and then stack top, and then followed by R, and then stack top. Okay, so let's explore the key points one by one. So the kernel entry point. The execution of the kernel starts at the boot function, okay, which is specified as entry point in linker script. This function stack pointer sp is set to the end address in this function. stack pointer. Is it this one? The stack pointer, kernel entry point. Is it this one? The stack pointer SP set to the end address of the stack area defined by linker script. Jump to the kernel main instruction. Kernel main instruction function. It's important to note that the stack grows towards 0. It means decremented as used. Therefore, the end address, not the start address of the stack, must be set. End address of the stack. So we're moving. Set the stack pointer to the end address, and then jump to kernel main function. Right? Okay. Cause note that the stack grows towards 0. So note stack grows towards 0. Therefore, when we use stack, it decrements as it is. Yeah. So the boot function attributes here instructs the compiler not to generate unnecessary code and before function. Okay. Yeah. No. Tells compiler no generating unnecessary code before and after function. As the text attribute which controls the placement of the function in linker script. Since simply okay. Yeah. Makes sense. Controls the placement of the function. Sets the function at the text.boot section, which is where OpenSBI jumps to, which is this hexadecimal address here. Then extra char over here, get linker script symbols. At the beginning of file, each symbol is defined. In the linker script is okay. In obtaining in the linker script is defined using external char. Just declare it. Along the value of the 0 byte of the start address. It's recommended to add careless mistakes. Yeah. Obtaining. Yes. Char type is not that important. Yeah. Yeah, it's different. If you declare char is that, but not the curly bracket is different. BSS section, initialization. Yeah, there it is. This section over here. Yeah. So this one basically, so it initializes, sets the BSS section to 0. Yeah. The memset, it basically writes. Not sure why this is an error over here. Oh, sorry. Writes C into buff, specifically for stacks. With the size n. Yeah. There you go. While n is decreasing, which is basically the size, because size end minus the first is the amount of things to write. So just writing, well, n size is decreasing because it grows up. Pointer, as it grows up, pointer puts in that. Yeah, it's basically the pointer. Alright, you're putting because you can't write directly to the buff. We're casting the buff into an unsigned integer, and then we make a pointer to it, and then we can write character, the char C into the buff as we go along. Yeah, because the pointer as we go, it goes up, right? While the number ends. Yeah. Because the n decreases. Well, the n decreases because if it decreases, yeah, the stack grows when the n decreases. So we're writing it. Reference by the P. Yeah. Then we're gonna run. Yeah. And then we're gonna put into the run file. So this is gonna be our bars command. So here are some more variables. So CC, okay, which is the cross compiler, if you could use it that way. We can just use clang, right? If I can, or maybe I could in theory just like, but I could just use like /clang. That's all, because we don't really. And then the C flags is it gonna explain? No, it will explain C flags. Yeah. And then I will probably add some notes section. So C flags. So it's the STD standard. Okay, so standard version of C is gonna be C11. That's the standard. I'm not sure about 02. Is it 02 or 02? That looks like O. That's not like O to me. Yeah, and then G3, W all, W extra. So what is 02? 02 is enable optimizations. C flags explained. Use, okay, we're gonna left to right. Use C11. Enable optimizations. Enable optimizations. Right. G3. Max amount of debug info. Major warnings. Additional warnings. Let me just. Okay, so then extra target equals risk 5, 32 unknown elf, unknown, yeah, okay. Fuse LD is equals to LLD, which is the linker. And then the fno stack protector, f freestanding, no standard library. So additional warnings, right? Compile for 32-bit RISC-V. Freestanding is no std lib for host n. Use LVM linker. Disable cherry stack protection. No standard library. I'm not sure about that one. I didn't type that in, did I? Okay. Oh, yeah, there you go. Then build kernel, which is CC, C flags, WL, T kernel LD, WL map equals kernel.map. Output is kernel.elf. Then kernel.c. WL passing right, clang, yeah, clang is the compiler. Um, W. Okay, so this is the linker. Specify linker script and WL map equals kernel map. Output a map file, which is the linker allocation result. Basically, how it allocates memory, and no reboot. I guess we can write it that way. Second line, kernel is kernel.elf. Yeah. So that should be it. Modify run dot. Yeah. Then terminal. Where's the terminal? Yes. When you run, shit. Sorry, there shouldn't be any space there. What did I do? Type something incorrectly. BIOS default graphics serial. Clang, yes. Freestanding. Oh, I seem to have left something. Is it in the QEMU? No, it's just clang. Clang. Output. Put kernel.elf. Map. Okay. What did we do exactly? What did I write wrong? CD. Where is CD lib? Yeah. C flags. Kernel dash map. Kernel.elf kernel.c. Wait. What's the problem? Or is the shell, does the shell not support it? Oh, there we go. Okay. Let me change this to change logs. It boots! Yay! There we go. Guys, we just built our kernel. It seems to have booted up. Yes, it's now on an infinite loop. Boot. Yes, and this one should be I think we should put this in 31st. Yeah. Put both of you in there. Yeah. Yeah. Works properly. And because infinite loop as defined in kernel.c, that is 4, which is yes. If I check here, this is the loop. Loop. This is the loop. Go. Okay, so when it says when you run, when it says the kernel enters into infinite loop, there are no indications that kernel is running currently, but don't worry, this is quite common for low-level development, where key debugging features come in. To get more information about CPU registers, open key monitor, which is control, I forgot. Shit. What do I have to do? Control A, C, and then type info registers. This is the info registers. If you go to PC, there we go. It points to the, shows the current program counter. Yes, an address of the instruction being executed. Okay. Yeah. Good. So the program counter is there. Each line. PC. Yep. Current the address of the instruction executed. Let's use the disassembler. LVM obj dump. Narrow down the specific line of code. Kernel.elf. Okay. And 48. So if we go, so earlier it says 48, right? This is the address, right, that we saw, right? Yes, disassembled instructions. PC is currently running. The currently executed instruction is at here. Key must reach the kernel main function. Yes! Yes! Did it. If the stack pointer, SP, set to the value stack top. So the stack top, we're gonna check the kernel.map file here. If we check the kernel.map, the stack top, so the SP register is set to the value of stack top. Yeah, should be somewhere here, isn't it? Stack top is dot here, right there. Check the kernel.map file. Yes. SP2 x2 xp. Yeah, there it is. First column, the address where they placed virtual memory address. We can see that the stack top is placed there. Confirms that the stack pointer is currently kept to the boot function. Where is the boot function? The boot function is it boot function, the boot function is the boot function yeah 24, not sure where it is. It's a stack top. stack top is set at that confirms point that the stack pointer is set correctly. Yes. Execution process inferences will change. If you have determined, yeah. There you go. We're done. We just wrote our first kernel. Hello world will be for tomorrow. I'll do that tomorrow. Cool. Let me push everything. Added some change logs, notes. Works well. Yeah, because the stack pointer, move stack pointer. Yeah. I'm not sure if you can see the. I'm not sure. You can check the VMA. Yeah. Yeah, text, correct. Yeah, that's where the stack top is supposed to be. Done. Alright, and if I go check on my repository, yeah, there you go. That's my RISC-V kernel. Perfect. Okay, let me add change logs to my. Go here. Edit change log. Yeah. Good. We're done for today. I wrote everything down there. Yeah. So the reason why I wrote a lot of notes there is because I wanted to make sure that I understand everything. So yeah, good. Thank you. Thank you everyone for watching. No one's really watching this. Thank you that I'm recording this for myself in the future. Right. See you later.